We're going to start our discussion on wide banding techniques, and we'll devote quite a few lectures to this topic. Today we shall discuss the introduction to wide banding techniques and how inductors can be used. Obviously, if you want to use inductors, it cannot be an integrated circuit. It has to be a discrete circuit or an IC chip with an inductor added from outside. Okay. But before we take up this, there are a couple of circuits that are left in tuned amplifiers, which I want to draw with you. I said that if you want to sharpen the single tuned amplifier response, then you cascade a number of them. If you cascade two of them and keep the normalized magnitude as 1, then naturally the response will sharpen like this. And if you cascade more of them, then it will become sharper and sharper. And we'll show, well, we'll come to that relationship later. But we showed last time that even coupling two tuned circuits, even using two tuned circuits in a single amplifier, single transistor, poses problems due to C mu. This is the menacing problem in the design of any high frequency circuit. So I say there are two modifications that exists in which the effect of C mu is minimized, and the first one is a cascode, and the other one is a CCCB combination. In the cascode stage, one transistor sits upon the other, and the circuit is this. I am not drawing the biasing circuits, only the AC part of it. Q2 sits upon Q1. The base of this is grounded, and to the collector of Q2 is connected one tuned circuit. Let us say R2, L2, C2. And here is the output voltage V0. Now you know how R2 is created. R2 may not be an externally added resistance, it may be the loss component of L2. That is, L2 is in series with RS2, which is equivalently made into a parallel circuit like this. And the other tuned circuit is in the base of Q1. That is, I am only drawing the AC equivalent circuit. So you have an R1 and L1 and a C1, where R1 takes care of the internal resistance of the source I sub S and also the losses of L1, okay, and the biasing resistors RB1, RB2. What else? It also has to absorb R pi 1. All right, all these combined make up the resistance R1. Now, the reason why C mu cannot affect the performance of this circuit substantially is the following, that the impedance between this point and this point is R pi divided by beta plus 1, and therefore the impedance is approximately 1 over GM, and when you multiply by GM RL, it becomes equal to 1. So 1 plus GM RL becomes 2. So at the most what is reflected here is 2 C mu. Agreed? No further deterioration, and C1 can then be correspondingly reduced to take care of 2 C mu.
So is this Q2 biased properly?
Yes, Q2 has to be biased properly. It has to be. That is the same collector current. The Q2 and Q1 have the same collector currents. Okay, that's why the GMs are equal.
But there is no resistance in the base. So
there is no resistance in the base, and therefore it is biased. It is biased from the emitter side. Okay, maybe there is a negative supply here. That is taken care of. Okay. Now the question that may arise here is that the impedance between these 2 points is not just a resistance. There is a C pi 2 of Q2. But what does C pi 2 come as? C pi 2 comes as the load, it comes as C pi 2 multiplied by beta plus 1. So it comes as a large capacitance. A large capacitance, the shunting effect of R pi 2, a large capacitance means low impedance, and therefore the load that Q1 faces is approximately 1 by Gm shunted by C pi 2 beta plus 1, and usually 1 by Gm is smaller than this impedance, and therefore that dominates. Okay. The other thing is, what about the C mu of Q2? Well, as you see, C mu 2 is from the collector to the base, and therefore it simply adds to C2 in parallel. Agree? So C mu does not have much of an effect here, and if these effects are taken into consideration, that is, if you use a trimmer here, a small trimmer here, okay, or maybe C1 itself is variable and C2 itself is variable, then you can tune the two circuits to exactly the same frequency, and you can get a sharpening of the frequency response. The other circuit is the CC CB combination, and this circuit is the one that is preferred in ICs because its configuration is exactly that of a differential amplifier. Okay, the configuration is like this. This is the CC circuit, and the CB is coupled to it through the emitter, that is, which is exactly that of the differential amplifier, and they are biased by the same kind of arrangement, namely there is a current amplifier here, there is a current source here, okay, exactly like the differential amplifier, and the second tuned circuit is used here. This is L2, C2 and R2, which goes to plus VCC. Okay. Again, the C mu of Q2, the C mu of Q2 simply shunts C2, so it can be taken care of. There is no Miller effect. The C mu of C2 of Q2 from here to ground is simply, this point is AC ground, and therefore it simply shunts C2. And the other tuned circuit is here at the base. In other words, I am not showing the C1, R1 and L1. Okay. Is this a total biasing? Is any other biasing considerations needed here? Nothing is needed, because this point, as far as this is concerned, it's grounded. Okay. So this is a perfectly biased circuit. It will work, and this is available as a chip, including the current source. That is, two matched amplifiers, two matched transistors, and a current source. This is available as a chip. These two you have to add externally. Okay. Now, as I said, C2, C mu 2 only affects C2. What about C mu 1 between the base and this point? The load here for the CC stage is 0, and therefore C mu reflects simply as C mu. That's all. Okay, which can be taken care of by C1. So these are two circuits for getting a sharper response from two identically tuned circuits. Two tuned circuits, identically tuned, having identical characteristics, and therefore they sharpen the response. Now there is no reason why you cannot cascade more than two. Okay, more than two. For example, the CCCB cascade, the CCCB cascade, can you use another CCCB in cascade? That means, can you use 4 such tuned circuits? Obviously this cannot be coupled directly to the next stage. Why not? Because then this tuned circuit shall be affected. So what you do is you put an emitter follower here, again a common collector stage, one common collector stage, and then another CC CB combination. Okay, you can get 4 of them, and 4 of them will make it much sharper. It can be shown that if n such stages are cascaded, n stages, each of which has a response like this. If n such stages are cascaded, each of which has a response omega 0 and the bandwidth is B. If this is 1, then this is 1 by root 2. If n stages are cascaded without interacting with each other, that is in a non-interactive manner. What does it mean? One tuned circuit does not affect the performance of the other tuned circuit. If they are cascaded in a non-interacting manner, then the resonance frequency omega 0 n, that does not change, right, because they are all tuned at the same frequency. So this is omega 0, but the bandwidth Bn changes, it shrinks, and the shrinkage factor, it can be shown that it is the bandwidth of one stage multiplied by square root of 2 to the power 1 by n minus 1. This is the rule for shrinkage, and it can be very simply derived. I'll indicate the steps in the derivation a little later, but let me give a name to such a cascade. A cascade of, yes?
It should be divided by bandwidth is increasing or?
No, it's decreasing. 2 to the power 1 by n. If you have n equal to 1, it is 1. If you have n equal to 2, it's 0.41 square root, which is 0.6. So this is shrinkage factor. Okay. How it is derived, I will come a little later, but there is a name given to this. All tuned circuits are tuned at the same frequency, and this is called, such cascades are called synchronously tuned stages. Synchronously tuned stages. The derivation of this is extremely simple. If you remember that for one tuned circuit, the transfer function is of the form, for the simple RLC circuit, the transfer function is of the form S divided by S squared plus S by, pardon me? S into R by, now I don't want to put it in this form, I want to put it 1 by LC. So it was S by RC, isn't that right? Pardon me?
Can you please repeat what this thing is?
This is the transfer function of a simple single tuned circuit, is of this form, isn't that right? S squared plus, yes, it was a band pass filter, which I can write as, let me write the normalized value, that is I want to make the maximum equal to 1 and then 1 by root 2. Okay, so I will write this as S by RC. Agreed? The normalized value. What is the problem? For a simple tuned circuit, well, let's derive this. I see that you are not comfortable. This is what it is. So I have the V0 by I would be equal to the impedance of this, which is 1 by R plus SC plus 1 over SL. So this is equal to SLR divided by S squared LC plus S squared LCR plus SL plus R. Agreed? Which I can put in this form. That you can easily see. Isn't that right?
Sir, in the cascading of these stages, it is implicit that all the stages should have the same center frequency omega naught.
Correct. That is why it is called synchronously tuned. Okay. So this is the expression. I want to simplify.
So
we don't get this.
You don't get this?
So
the whole numerator.
No, I don't. In the numerator, I don't get it. What I am doing is I want to normalize this. I can write this. The denominator, I can write it like this. Then a constant multiplied by s by r. I can do that. What I want to do is to write it in normalized form so that I don't have to deal with individual tuned circuits. I can deal in general. In general, my normalized response would be s by b divided by s squared plus s by b plus omega naught squared. Okay? And what I am trying to do is to multiply, is to cascade n such stages. So to the power n, which means that to find out the bandwidth Bn, I have to solve for this expression omega squared by b squared divided by omega naught squared minus omega squared whole squared plus omega squared by b squared. Okay, this is the magnitude. This is the magnitude squared of the inner expression. Agreed? Or have I done it too fast?
Yes, so you
Putting s equal to j omega and taking the magnitude.
So how did you get whole to the power n term?
Because I am cascading n such stages. I am cascading n such stages, so the transfer function will be h1, h2, h3, h4 and so on. Okay? And this is the magnitude squared of the inner expression. If I raised it to the power n, then how do I calculate the bandwidths? This should be equal to? No. I have already taken a square.
1 by 2.
1 by 2. So solve for omega 1 and omega 2 from this expression and find out Bn as equal to omega 2 minus omega 1. You will see that it simplifies to the expression that I had written. That is Bn equal to B1 square root of 2 to the power 1 by n minus 1. I leave that algebra to you. Okay. Now there is nothing sacred about synchronous tuning. Suppose you have asynchronous tuning, that is two responses, one is like this and the other, let's say, is like this. Their maxima are the same. Their maxima are the same, or maybe we normalize this to make them the same. Okay. So if I multiply these two, what I am going to get is something like this. Okay, where this top can be shaped depending on the difference between the two resonance frequencies. For example, if they are pretty far away from each other, then perhaps what I will get is something like this. I will get two peaks like this and a dip in between. Okay, I can bring them closer and get something like this, a flat top. Such a response, a flat top, such a response is preferred in circuits which have to pass a band of frequencies, not a very small band. It's not just one single frequency omega 0, but omega 0 plus minus delta omega, as is required, for example, in an IF amplifier. In the IF amplifier, yes.
What is that central blue line which you have drawn?
Oh, this is the result of these two.
Or should it be lesser?
Oh, I have not normally. If I normalize this, then it will come up to 1. Okay, it will come up to this. If I normalize this, okay. Otherwise, it can go higher or lower. But let's normalize. All right. So this composite response can be either double peak, or it could also be like this, single peak, if they are brought very close to each other. For example, if they are coincident, then you know it will be a single peak. If they are slightly separated, then I will get this Curd selectivity, I will get better, but the top may become flat. Such a response is preferred in the intermediate frequency stage of, let's say, an amplitude modulated receiver. a receiver which has to receive amplitude modulated transmission. You know that the bandwidth is the carrier frequency plus minus the modulation frequency. So you require a band of frequencies to be transmitted, and such a response is always preferred. It usually what is done in an IF amplifier is it is the two tuned circuits are coupled magnetically. That's another possibility. For such responses you can have, let me draw this. You can have a single transistor which has a tuned circuit and another tuned circuit which is coupled magnetically. Okay. And you take the output here. This is a way of stagger tuning. All right. Since the two frequencies are not required to be identical, you can tune one of the capacitors so that the desired response is obtained, so that the tuning is staggered. That is, the resonance frequency of this circuit is not the same as that of this circuit, but their coupling is through magnetic coupling. Okay. As you bring the two tuned circuits closer together, as you tighten the coupling, the double peaks appear. There is a critical value of coupling, critical value at which it would be maximally flat like this, and this is called the stagger tuning. Okay. Both increase the skirt selectivity, that is, they sharpen the response. One, the synchronous tuning is used when you have a very narrow band, whereas stagger tuning is used when you have a larger band to be tackled. We shall perhaps take some examples in the problem session. We now go over to wide banding techniques. As I said, the sequence was, first we did with oscillators, then we went to narrowband amplifiers, now we are going to wideband amplifiers. Okay, if you recall the RC coupled amplifier, can you see the circuit on the screen? Can you see the circuit on the screen? I have redrawn the RC coupled amplifier. If you recall the RC coupled amplifier, we required three capacitances, CC1, CC2 and CE. Two, what are these? Coupling capacitors or blocking capacitors. They are also called blocking, and this is a bypass. All right. The effect of this is that the low frequency response, can you see this on the screen? The low frequency response, the DC response is 0, and then it rises to a certain value. It remains almost flat over a certain band of frequencies and then falls down again. The high frequency fall is due to the internal capacitances of the transistors. Okay. That is C pi, C mu and C naught, or C, D, G, then C, CGS and CDS. Okay, the three capacitances of an FET. Now, as far as FL is concerned, the low frequency 3 dB point, as you know, these are determined by all these three capacitances together. All right. But the usual design that we do is two of them we make very high, okay, and one of them is used to control the FL. As far as integrated circuits are concerned, as you know, we cannot use a capacitor. That's barred. We cannot use a capacitor. We cannot make it, that's period, such a large capacitor. So what we do is we make coupling direct. Isn't that right? We make direct coupling, no capacitor, and therefore as far as IC amplifiers are concerned, they all start from DC. That is, the frequency response is that of a low pass filter. Is that correct? This is a band pass. Now one can argue, why can't we use the same techniques that we use for ICs in discrete circuit design? Why can't we use the same techniques? What is the problem? Can anyone point out? I have already discussed this.
What is the question? Can you repeat it?
The question is, in integrated circuit we don't have to bother about FL because we don't use a capacitor. So our response starts from DC. Why is it that in discrete circuit design we do use these three capacitors? Why can't we use the same techniques as we use for integrated circuits in discrete circuit design? Why not? Size of the circuit. No, size of the circuit can be bigger because we can use capacitors, but capacitances are costly. Why can't we get rid of these capacitors?
So they require bigger resistances on the. So they
We
can't-
require bigger resistances.
So here in R1 or 2 only.
All these can be avoided. You see, the basic problem.
So we have a DC part in the output which we want to block. We only want a pure AC output.
Oh, that problem is there in ICs also. We get rid of that by level shifting. We get rid of that by class B operation. Okay, it's also there. The basic problem is, if you recall how integrated circuits were biased. What was the biasing? Basic
Current
technique,
mirror.
current mirror. And what does current mirror need for its success? It needs for identical transistors. They are made on the same chip by the same processing steps, and therefore the transistors become identical, so that if VBE is identical, I sub C is also identical. Now that is very difficult to achieve in a discrete circuit. Hardly ever you get two transistors which are identical. Hardly ever. Even if you couple them so that VBEs are identical, the collector currents are not identical. Besides spread of other values, hardly ever you can make two transistors, two discrete transistors identical, and therefore IC techniques cannot be used.
So, but in case of a Widner source,
Mhm.
we don't need the two transistors to have the same kind of properties.
Of course we
same
do.
BB.
Yes, the saturation currents have to be the same. They have to be identical. There is no other way. Okay. So it is a fact of life that in discrete circuit design we have to use these three capacitors, and if you want to make it wideband, that is, if you want to reduce FL, and this is where a stereo amplifier, a quality stereo amplifier costs. If it has to go right up to fraction of a hertz, it costs a huge lot of money, because the capacitors that are used that have to be high valued, and they have to be very high quality capacitors, and that is where you pay the money if you want low frequency response. Well, if you don't want, then hell with it, no problem. Okay. So in discrete circuit design there is nothing that we can do about the low frequency problem. You have to use high quality, high valued capacitors. You have to pay money. In integrated circuits that is not a problem. So in integrated circuits the problem is that of FH. How can you extend FH? That is the widebanding technique, and we shall discuss several techniques to make a wideband amplifier.
So what is the high quality capacitor?
High quality capacitor is a capacitor which is very little leakage. Okay, leakage, that is the parallel conductance. Almost all capacitors, if you put across a multimeter, a electrolytic capacitor for example, it will not show infinity. It will show a current because there is a leakage. Okay. Now, so widebanding basically means extending FH to higher frequencies, and this can be done by various techniques. We shall discuss a selected few of them. One is widebanding techniques. One is use of inductors. Obviously you can't use it for ICs, you have to do it, you can do it only for discrete circuits. If it is to be IC, then you have to use the inductor externally. Okay, use of inductance, and then use of compound devices. An example, two examples of which we have already seen. The cascode is two transistors, and the cascade of CC/CB. Such compound devices, because they kill Miller effect. You see, Miller effect is the main problem in FH. How is FH determined? FH is 1 over 2 pi for a single transistor amplifier, R pi multiplied by, yes, CT T, that is the total, which is C pi plus Cm. It is this Cm which creates the problem. It is a large capacitor which can swamp C pi, because Cm is gain multiplied by C mu, and therefore if we can get rid of Cm, obviously the high frequency end shall be extended. And two such compound devices we have already seen, the Cascode and the CC-CB combination. We shall see, we shall look at them in greater details at a later point of time. We will analyze them and see how they extend. Then the third technique is use of feedback. This we have already explained, that negative feedback increases FH and decreases FL, and therefore negative feedback can be used for wide banding, but the price that you pay is a reduction in gain. Okay, we will see how negative feedback can be used locally, that is for a single transistor. What techniques you know of single transistor negative feedback? Unbypassed emitter. Anything else? You know another technique. Not cell biasing.
Base and collector are joined.
Yeah.
Base and collector are joined through a resistance, and the emitter resistance is 0. Emitter is connected to ground. Okay, so you can use either local or you can use overall. For example, you make a 3-stage amplifier and then make an overall feedback. It could be series shunt, one of the 4 configurations. So use of feedback is one. Then we will show that the differential amplifier technique that is so popular in integrated circuits, op amp and every other circuit uses a differential amplifier. This differential technique can also be used for wide banding. So differential technique. And another technique which has come only recently, differential technique, will show this circuit later and make a detailed analysis. But another technique which has come only recently and is gaining greater and greater importance is signal processing based on not voltage but current. So current processing. And we will see that in current processing rather than voltage, you see in current processing, if you have a resistance in series with a capacitance and you pass a current through this, you force a current, that current is not going to depend on the capacitance. Do you see the basic idea? If you take the voltage across the resistance, then it will obviously depend on the capacitance. But if you force a current, then the capacitance effect, capacitance loses its teeth, and therefore current processing can obviate some of the disadvantages of voltage processing, voltage signal. And we will see at least one example of this, the so-called Gilbert cell. This is an IC chip that is available for wide banding technique, wide banding amplifier. Now let us first look at the use of inductance, and a very simple circuit that can be used for this purpose. I will not show any biasing in these discussions. One of the very simple circuits which has been popular in the early stages of transistor circuit design, and it is based on a similarity with valve circuit design, is that you use a transistor in which the base, in the base you connect an inductor. An inductor cannot be made without a resistance, and therefore LR, and let us say the impedance let us say the it is a current source drive. Okay. Now one should be able to understand immediately how this causes wide banding. Now why did we connect this in shunt? LR, this should show, no, not only current source, I mean if you have voltage source here, of course this is ineffective, correct, and therefore we have connected, but why did we connect in shunt? What is the impedance, effective impedance between these 2 points? R pi and CT. Isn't that right? R pi and CT. And if we connect an inductance, obviously what we are trying to do is to make a kind of a parallel resonance circuit. Alright? That is, we are trying to annul the effect of Miller capacitance by using an inductance in parallel. So some of the reactance of the capacitance is being cancelled. Now we are not resonating, however. Why not?
Because you want high band.
Because we want a wide band amplifier. We don't want a picking. We want as flat as possible, up to as high a frequency as possible. So we are using an inductance to reduce some of the effect of CT, the reflected capacitance.
So, but if you use an LC circuit, you are inevitably going to have peaking.
No, not necessarily. We'll use an appropriate value of LNR so that there is no picking. We'll take care. In fact, we will attempt to make it maximally flat. That is, we will attempt to make it maximally flat like this. What should occur with a careless design is maybe something like this, that there is a picking and then it comes down. We don't want this. We want as flat as possible. Okay? We'll see this. Number 2, why a parallel LR? Why not a series LR? We could also cancel some of the reactance by taking a series LR circuit, okay, by making a series kind of resonance. Well, as we shall see through an example later, that series resonance is less effective than parallel resonance. Usually series resonance is less effective than parallel. Well, it's not resonance. Let's say, what should I call this? Let's call this a shunt picking. That is, a coil is connected in shunt. It's called picking, although we will not allow picking. We will suppress the picking. Well, if I use an LR in series, this is called a series picking. Both circuits are used. That is, an inductance, a coil, is maybe used in series or maybe used in shunt. Next point, can I replace this inductance by a parallel inductance and a parallel resistance? Sorry, no. Why not? Because that equivalence is valid only at the resonance frequency, at a single frequency. Here we are concerned with wide band, so that complicates analysis. This R has to remain as R. We cannot replace it by a parallel resonance. Parallel LP-RP combination. May I repeat the reason? The reason is that our operation shall be over a wide band of frequency. It is not a single frequency operation as in a tuned circuit, as in a tuned amplifier, or a small band of frequencies around the tuned frequency. So we cannot replace this by a parallel circuit. And all we have to do now is to draw the equivalent circuit. And the equivalent circuit is this. If you draw it carefully, you have an LR. Then let's not ignore Rx anymore, because we are going to very high frequencies, and at very high frequencies the capacitor reactances may be comparable to Rx. Wherever inconvenient, however, let me warn you, we shall throw out Rx, wherever inconvenient. It's possible to take care of it here, so we are saying, fine, we will respect you. We will respect your position. And then you have the R pi and the capacitor CT. We use the Miller effect to simplify the circuit. This voltage is V pi, then we have GM V pi, current source in series with RL, and this is the output current I0. We wish to find out I0 by Is. Okay? We wish to find out the transfer function I0 by Is. In order to do that, we apply Thevenin's theorem to the left of this black line. Okay? And we get the voltage source as Is times R plus SL. Alright? And in series with R and L. Alright? Once we do that, then V pi can be obtained by inspection and the current I0 is equal to minus Gm V pi. Is the point clear? Okay. So, if I do that, you see that I0 is equal to minus Gm V pi, which is equal to minus Gm Is R plus SL, this is the voltage source, multiplied by the impedance R pi divided by 1 plus S R pi Ct divided by the sum of the 3, that is R plus SL plus Rx plus R pi divided by 1 plus S R pi Ct. Have I written down correctly? I found out the current first, then multiply by the impedance. That's right. So, this, as you can see, Gm and R pi combine to make minus beta, okay, minus beta, and then I want to find out the transfer function I0 by Is. So, if I multiply by 1 plus S R pi Ct, then I get in the numerator R plus SL divided by, in the denominator I get R plus SL plus Rx 1 plus S R pi Ct plus R pi. Is that okay? I have forgotten something? No. Okay, I can write this as, I will now try to write it in a normalized fashion. I can write this as minus beta L, okay, I am taking L common, S plus R by L, and in the denominator let's collect terms. S squared L R pi Ct plus S L plus SL, then R plus Rx multiplied by R pi Ct, okay, the coefficients of S, plus R plus Rx plus R pi. Okay, I could have left the algebra, but I am doing the algebra for a specific reason. Later on I will not do this, I will simply say it can be put in this form. But what I want to do is, I want to put it as a polynomial in S in the numerator with the leading power 1, and a polynomial in S in the denominator with leading coefficient equal to unity. So, what I get is I0 by Is equal to minus beta L, I should take L R pi Ct, then I get S plus R by L divided by S squared plus S. Now what shall I get? 1 by R pi Ct, I am dividing by L R pi Ct, plus R plus Rx divided by L, and R plus Rx plus R pi divided by what? L R pi Ct. Alright. We shall call this as Z, which means that the transfer function has a 0 at S equal to minus Z. We shall call this as the coefficient A, and we shall call this as the coefficient B, and we shall call this as some value K. It is a negative value, L and L cancel, K is minus beta divided by R pi Ct. Essentially you see K is minus Gm by Ct. Agreed? K is minus Gm. Do you know what is Gm by Ct? We had given a name to this. Omega T. That's correct. It's a gain bandwidth product. Gm by Ct. Okay. Now, therefore, what I get is I0 by Is equal to K S plus Z divided by S squared plus AS plus B. Okay. Usually the inductance is such that A square is less than 4B. What does it mean? It means that the poles are complex. The poles are complex. Can the 0 be complex? No. This small z is a real quantity and therefore S equal to minus z. That's where the 0 is. The poles are complex. And if you write the transfer function, let's call the transfer function as AI, j omega, magnitude squared. I do such things by inspection, that is put S equal to j omega mentally and find out the magnitude squared. Obviously I shall have k squared omega squared plus z squared, alright, okay, divided by b minus omega squared whole squared plus s squared omega squared. If I have made a mistake, please point out. It's a magnitude squared. This I can write as k squared z squared 1 plus omega squared by z squared, and in the denominator I can write b squared plus a squared minus twice b omega squared, agreed, plus omega to the fourth. I am doing this very slowly because I am not going to do this again. Divided by b squared, I take b squared out, so that what I am doing now is to write the magnitude squared function as a ratio of polynomials in omega squared with the lowest power term, that is the constant term, equal to unity. So I am writing this as 1 plus omega squared by z squared divided by 1 plus a squared minus 2b by b squared omega squared plus omega to the fourth divided by b squared. Obviously, the response of this transfer function will depend on the relative values of a and b, right? And and a and b can be so selected that the response has a peak, or it does not have a peak. We don't want a peak because our purpose is to wideband the amplifier, so we must avoid this. How can we avoid this? We must choose a and b in such a manner, their relative values in such a manner that not only no peaking occurs, but we want a response like this. With peaking you can have a response like this. Without peaking you can have a response like this. No, I have it's the same color, I shouldn't. Okay. Now obviously what I should prefer is this response, because this goes down, it does not extend the high frequency range. I can extend right up to some frequency fH like this. I can also extend beyond fH provided I allow for peaking. I don't want that. Okay. So the red colored response, I want it to be as flat as possible, and the term for this is maximally flat. What is the criterion for flatness of a curve? Y equal to fx. What is the criterion for flatness? Dy dx should be equal to 0. It's either a maximum or a minimum. Now if I can make dy dx equal to 0 and d2y dx2 also equal to 0, obviously I have a second order of flatness. Now I shall show next time that for the red curve, for this particular situation, this is the best that we can do. We cannot get more than 2 flatnesses, and this flatness I shall assume at omega equal to 0. Okay. So, I want flat here first order and also second order, and that would be the red curve, which will be called maximally flat, or in short MFM, maximally flat magnitude, and this is what we shall explore tomorrow.